Welcome back. From today, we will start discussing continuous time Markov chains, otherwise known as continuous time Markov processes. Alright. So, what is a continuous time Markov chain? So far, we have studied DTMCs, discrete time Markov chains. If you remember, so for a discrete time Markov chain Xn, so the time index is n for a discrete time Markov chain, right? And as we know, we know that it satisfies probability xn given xn minus 1, xn minus 2, etc. is just probability of xn given xn minus 1, right? For any values of the states in the past, only the previous state matters, right? So, this is what a DTMC is. A CTMC or a continuous time Markov chain or a continuous time Markov process, as it is sometimes called, is something similar, alright. So, it works in continuous time. So, I will broadly tell you what it is. So, xt, okay, its time is now continuous, okay. Let us say t greater than or equal to 0, okay. So, it is what is this characterized by, okay. Before I give you a formal definition, so pictorially it is easy to tell you what it is, okay. So, that is time 0, okay, and this is continuous time, okay. A CTMC is characterized by something known as an embedded Markov chain, okay. So, it is characterized by two things. An embedded DTMC, okay, and two, exponentially distributed holding times in each state. Okay. So, a CTMC is characterized by an embedded DTMC and an embedded Markov chain and exponentially distributed holding times in each state. So, there is an underlying Markov chain called the embedded Markov chain, which is evolving. You can think of a discrete time in which the embedded Markov chain is evolving. Every time the Markov chain enters a particular state, the embedded Markov chain enters a particular state, the continuous time Markov chain stays in that state for an exponential amount of time. And then after this exponential amount of time, the underlying DTMC goes to a different state, and so does the CTMC. Okay, and again CTMC holds for an exponential amount of time depending on the state that the DTMC goes to, the embedded DTMC goes to. So, let me just draw this out. Let us say that I start with x naught equal to I, okay. Then there will be a exponential holding time, okay. Let me call this u1. This will be exponentially distributed with a parameter nu I, which depends on the state x naught equal to I. Conditioned on x naught equal to I, the holding time is some exponential random variable, which is parameterized by some nu I, okay, some positive number nu I, okay. Then after this exponential amount of time, the underlying DTMC goes to some other state, let us say x1 equals j, alright. This x1, the state that this underlying DTMC, the embedded DTMC transitions to, is independent of the exponential random variable that just happened, it is independent of u1, okay. So, the DTMC transitions to some, let us say some state j with some probability Pij. The Pij's are the transition probabilities of the underlying DTMC, the embedded DTMC. Again you have another holding time, okay. Let us call this u2, okay, and this u2 will be exponential with parameter nu j, okay, which depends, the parameter nu j depends on the state x1 equals j, right. And again the underlying Markov chain will go to some state k with probability pkj. This exponential nu j is independent of the next state, okay, and so on. So, this is how the CTMC proceeds. So, you have exponential holding times in each state, right, with parameter dependent on what state the Markov chain is in, the embedded Markov chain is in, and after that exponential is finished, the both the embedded Markov chain and the CTMC move to some other state j with probability Pij. Okay. So, this embedded Markov chain, so let me embedded. So, let us say Pij is the transition probability over some countable state space S, which we can by default take it as 0, 1, 2, 3 dot dot dot. So, we are looking at the embedded Markov chain evolving on some state space S, which is we are taking it as 0, 1, 2, 3 dot dot dot, and Pij's are the transition probabilities. Okay. These are the transition probabilities over some countable state space. Now, I want to define this CTMC as CTMC xt is a stochastic process mapping each non-negative time to I can say S, which is let us say 0, 1, 2 dot dot dot, such that x of t equals xn for Sn less than or equal to t less than Sn plus 1, S naught equals 0, and Sn, I have to tell you what Sn is. Sn is the sum of these exponentials, m is equal to 1 to n, and each un given let us say xn minus 1 equals I is exponentially distributed parameter some nu I depends on I obviously, and independent of, maybe I should say conditionally independent of all um and xm for m not equals I. Okay, so, this is the definition. So, let us revisit this. A CTMC is a stochastic process xt. For each xt takes one of the values xn, where xn is the state of the embedded Markov chain. Okay. So, just to draw this out in picture again. So, you have S naught equal to 0. Okay. This is your after a certain u1 amount of time, let us say this is S1, and then after u2 amount of time you have S2 and so on. Okay. Now, if you just look at this, so let us say this is Sn, let us say that is Sn plus 1. Okay. So, each Sn is equal to the sum of the first n ui's, all right, and each ui conditioned on the state xn minus 1 being equal to I, right. So, if you are in some, let us say you are in some state I here, the Markov chain is in some state I here, the underlying Markov chain, embedded Markov chain is in state I, and sorry, that is your Sn plus 1, that is exponential with parameter nu I, okay, and this exponential random variable is independent of the other u's, right, and it is also independent of condition on xn equal to I, it is independent of the other xi's, okay. That is what a CTMC is. Now, we for the DT and embedded DTMC, I mentioned that it evolves on the state space S. We are going to assume throughout that the embedded DTMC has no self transitions. Okay, sorry, we will assume that the embedded DTMC has no self transitions, that is P I equal to 0 for all I. Okay. We are making this assumption for the embedded Markov chain. That is because if the embedded Markov chain transition from I to itself, in the continuous time process the xt remains in I, okay, and you do not even see a transition really, right. So, if you really want to see a transition in the continuous time process, you want to enforce that the DT and embedded DTMC actually goes to a different state, right. Now, this is not a very restrictive assumption, and you can actually prove that if you do have a self transition also, you can just reduce it to a CTMC which does not have self transitions by just redefining the nu i's appropriately. So, this is not a very restrictive assumption. Okay. So, the nice thing about this is that A, you do not see, I mean, if you have self transitions, you do not see it in the continuous time process, you can't see it as a transition because the process continues to be in a state I. And the other is that there is a nice equivalence, if you do not have say this self transitions, there is a nice equivalence between specifying the exponentials ui and the Pij's, all right, and the sample parts of the embedded Markov chain xn and the ui's and the sample path of the xt process, right. There is a one to one relationship between the xt sample path of the CTMC and the xn sample path of the embedded Markov chain and the ui's, all right. The xn's and the ui's together will specify xt and vice versa, okay. That equivalence also follows if you make this assumption. This is not a restrictive assumption again, as I said, you can, if you do have PII non-zero, you can tweak the nu i's to make PII 0, okay, and the statistical properties of the process will remain the same, okay. So, this is an assumption we will make going forward, that the embedded DTMC does not have any self transitions, okay. So, what can be shown is that due to the memoryless property of exponentials, the following property follows. You can easily show this. For any states I comma j, any integer L and any times t greater than tau greater than t1 greater than t2 dot greater than TL, we will have, apologize, we will have probability x of t equals j given x of tau equals I, x of Tm is equal to some xsm for m less than or equal to L. This will simply be equal to P x t minus tau equals j given x of 0 equals I. Okay. So, what do we have here? So, this is some kind of again this is a Markov property in continuous time. Okay, that is why this is called a continuous time Markov process. So, what this property is saying, this you can easily show. So, that is time 0. I am looking at some times, what are these, right. So, I am looking at TL a whole bunch of times, right. So, let us say that is T2, that is T1, that is tau, and that is T, alright. These are all various points in time, right. I am looking at the probability that xt equals, so this is xt, that is x tau, and then you have a whole bunch of the process is in various states, x of t2 dot dot dot, right. We are looking at the probability that xt equals j given x tau equals I and a whole bunch of values for these states, right. What we are saying is that only the most recent conditioning matters, that is number 1, right. So, all the previous conditioning, these guys can be thrown out, right, that is what we are saying. So, conditioned on x tau, all the previous values are irrelevant, okay, and that is not all. It is as though, this is again because of the first property is the Markov property, the second is that it is as though time just begins at tau, right. It is as though you are starting the process x naught equal to I and you are looking at probability of x t minus tau being equal to j. It is as though the process just started, the 0 time of the process is at tau, okay, and this is true for any times t tau, t1, t2 etc., and for any 2 states I and j, okay, and this property follows from the property underlying Markov property of the embedded Markov chain and the memoryless property of the exponential random variables, alright. This you can easily show. Next, I want to show a simple example, let us say. So, MM1Q and the embedded Markov chain. As you know, an embedded, so an MM1Q has a server with exponential mu and a Poisson arrival process at rate lambda, and the arrival process is independent of service times, alright. We are assuming of course that lambda is less than mu, so that the arrival rate is less than the service rate, otherwise the queue will be overwhelmed. In this setting, if this is actually an MM1Q is actually a continuous time Markov process, alright, and the embedded Markov chain is just the number of customers in the system, okay. So, the embedded Markov chain can be thought of as the transitions from xn minus 1 to xn in the embedded Markov chain happens either upon an arrival or a departure, alright. So, here the state space is again 0, 1, 2 etc., which is the number of customers in the system, and what kind of, let us look at what kind of transitions are possible, right. Let us say there are, let us look at P01, okay. This is the for the embedded Markov chain transitions, right. So, this is for the embedded DTMC. P01, see if you are in state 0, the only state you can go to next, right, is 1, right, because you have to from state 0, remember there are no self transitions in the embedded Markov chain, right. So, the queue is in state 0, the only non trivial transition it can go to is 1, right. So, P01 is 1, right, this is the embedded Markov chain, remember, right. But if you look at P10 for example, so there is already one customer in the system, right. What is the probability that the next transition, the embedded Markov chain, which corresponds to the evolution of the number of customers in the system. So, you are looking at the probability that the system goes from having one customer to having no customers, right. This happens if the customer in service completes his service before the arrival of the next customer, right. Remember that the customer in service, this one person who is in service, has an exponential service time of rate mu, right, and the incoming customers are a independent Poisson process of rate lambda. So, there is a competition between the service exponential, which is mu exponential, and this arrival exponential, which is a lambda exponential. Of course, these exponentials are independent, right. So, the probability that the service exponential wins is nothing but mu over mu plus lambda, right. This we already know from our first initial study of Poisson processes, right, independent exponentials, racing exponentials if you will, right. So, and so on, right. Now, if you look at what is P12, right, you are looking at now there is one person in service, instead of that person leaving first, you are looking at the probability that in fact there is a new arrival before the service of the first customer completes, right. This is obviously lambda by lambda plus mu, right. It is simply 1 minus the probability that the service exponential wins, which is the probability that the arrival exponential wins, which is lambda over lambda plus mu, and so on, right. So, now you can P 3, 2 and all is not very different, it is the same story, mu over mu plus lambda and so on, right. So, if you look at the DTMC, which is the embedded DTMC, you get a structure like this. This is the embedded DTMC. So, from 0 you can only go to 1, because we are not allowing self transition. Please remember that transition from 0 to 0 is not counted. So, the process remains in 0 and the only next distinct transition that can happen is the arrival of a new customer, right. So, this has probability 1, okay, this is in discrete time, and of course, this probability is mu over mu plus lambda, that probability is lambda over lambda plus mu, that is mu over mu plus lambda, and so on. So on. So, this is the embedded DTMC for the MM1 queue, okay. And what are the new I's? So, these are the PIJs, okay. And so, what are the new I's? If you look at this new, so if I am in state 0, right, new 0 is simply lambda, right, because if I am in state 0, I am waiting for a new customer to come in, right. So, what is the amount of time I wait until a new customer comes in to an empty system? It is exponential with parameter lambda, correct. So, the rate at which I transition out of state 0 is lambda. Now, what is nu 1? Nu 1 corresponds to the rate at which I transition out of state 1, right. So, how long do I stay in state 1 is the question. So, I stay in state 1 until either there is a new arrival, in which case I go to state 2, or until the person in service completes the service, right. That is exponential with rate mu. Now, so there are two competing exponentials, right. So, the total rate at which I get out of the state is, or the the amount of time I spend in the state is exponential with parameter lambda plus mu, right. In fact, you can argue that nu I is equal to lambda plus mu for all I greater than or equal to 1, right. First state alone I am waiting for the lambda exponential to fire, waiting for an arrival. In all other states I am waiting for either an arrival or the service to complete, right. So, there are two competing exponentials. So, nu I is lambda plus mu, okay. So, I have completely for the CTMC corresponding to an MM1Q, this is the embedded Markov chain and these are the nu I's, okay. I hope this example is clear. Of course, you can now solve for the embedded Markov chains, embedded DTMCs, steady state probability you can easily determine by writing out the balance equations, right. In fact, if you look at this DTMC, you can clearly see that this is a birth death Markov chain. The embedded DTMC is birth death and you can actually just easily write down the balance, local balance equations and figure out what the pi's are, right. In fact, for the embedded DTMC you will have pi 0 is equal to 1 minus rho whole divided by 2 and pi n is equal to 1 minus rho square over 2 rho to the n minus 1 for n greater than or equal to 1, where rho is just the load on the system lambda over mu, right, which is assumed to be less than 1. Okay. This you can easily solve. Okay. Now, what does this pi n represent? Okay. So, in the discrete time Markov chain, of course, pi n is the steady state probability of being in state n, right, of there being n customers in the system. Okay. But in the continuous time Markov chain, this pi n does not represent the probability of there being n customers in the MM1Q. Okay. This pi I represents the number of transitions going into state n. Okay. This is not the fraction of time spent in state n. I want to make this very clear. See, it's see you have different news, right, different holding times in different states, right. So, this pi I is the steady state probability of the embedded Markov chain, which represents the fraction of transitions that take you to state n. And because these nu I's are different, there are different holding times in different states, these may not represent the fraction of time spent in state n in the continuous time process. Okay. Note, pi I obtained, let us say as above, by solving the balance equations for the embedded DTMC represents the fraction of transitions into state I, maybe I should just say pi I, like that, state I in the CTMC. See, in the DTMC case, the fraction of transitions into a state is also the fraction of time spent in that state in the DTMC. In a CTMC, that is not true, right. The fraction of transitions that go to a state I is not the same as the fraction of time spent in the state I, because some of these nu I's are different from the other nu J's, right. So, you have to weight them appropriately to get the fraction of time spent in each state. So, we have not gone there yet. Okay. I am only talking about the pi I's. If you solve the DTMC, embedded DTMC steady state probabilities, you get some pi I's, some probability distribution over the states, What does this represent? It represents the fraction of transitions into state I. It does not represent the fraction of time spent by the CTMC in state I. Okay. So, of course, in all this I am assuming that the embedded DTMC is irreducible and positive recurrent, so that I can solve this pi p equals pi and get some pi i's, right. And the pi i's you also obtain are the fraction of transitions in the CTMC going into state I, and it is not the fraction of time spent by the CTMC in state I. Okay. And this, what is the fraction of time spent by the CTMC in state I, we have to work out separately. Okay. That is an important topic we will get to later.